Let's do that. Started recording.
Started recording?
Very tired.
It's working?
Tired.
Now it's working? Good morning, everybody. First, I would like to thank the organizers for giving me this opportunity to present my work here. And my sincere thanks to Aparna for allowing me to borrow her laptop, because yesterday my laptop just gave up. It didn't boot up anymore. So thanks, Aparna. Okay, anyway, so I will talk on dynamics of cell response in an elastic matrix in presence of external stresses. And my collaborators are Professor Sam Safran from Weizmann Institute of Science and Dr. Asaf Jelmus, who is now in Hebrew University. The work I will be presenting is a theoretical work, but we have strong collaboration with the group at Stuttgart, and specifically with Professor Ralf Kempkemer, Dr. Simon Junbauer, and Professor Joachim Spatz. Yesterday, actually, Margaret has shown us very interesting experiments. And we
might be a bit closer.
It's not. Now, it's okay? Same thing? I'll try to. Oh, okay.
No, that's happy. That doesn't happen.
It's okay. It's not. Okay, it's fine. So yesterday, Margaret has shown us very interesting experiments, and we all have seen that cells exerts a large contractile force to its extracellular matrix. And in fact, this is one of the classic experiments very early done in Harris and Harris group. Here the fibroblast sprayed on silicon rubber substrate, and the fibroblast pulls the rubber seed. You could see the wrinkle produced, which shows the cell exerts a large contractile force. Now, see a contractile force, its spreading, differentiation, different cell activity. Activities do not only depend on cell properties or biochemical properties of its environment, but also depends on the mechanical properties of the environment. We have already heard few lectures in the past few days, and specifically we'll hear about more in this session and also in the next lectures. So this is one of the very interesting experiments done in Dennis Disher's group at UPenn. And here, what they have shown, the differentiation of stem cell depends on the rigidity of the matrix. And depending on the rigidity of the matrix, it differentiates into various cell types. On a soft matrix, it developed into a branch neuron structure. On a tenfold stiffer matrix, it develops spindle-like muscle cells. And on a more rigid matrix, it differentiates into a polygonal cell bone shell. And this is actually a pictorial description of cells' mechanical environment. In our body, cells are always under internal and external forces induced by different interaction due to adjacent cells or muscle tension, or even they are under time-varying stresses. For example, due to periodic blood flow. And cell responds very differently in presence of static stresses compared to dynamic stresses. Now, I will show you a movie. Cells are on a substrate, elastic substrate, and the substrate has been stretched, relaxed at a frequency of 1 Hz for 8 hours. This is the stretching direction, and in absence of any external stretch, you could see cells are oriented randomly. They don't have any preferred direction. But once the external stretch is switched on, you will see cells orient away from the stretch direction and orient near perpendicular. This is the stretch direction, and cells orient away from the stretch direction. You could see that most of the cells are aligned near perpendicular. Okay, the stop says the switching has been stopped, and cells go back to the random configuration again. Now, in presence of static or quasi-static stress, cell orient parallel to the stretch direction. This is the stretch direction and cell orient parallel to the stretch direction. And I'll show one more example on the high frequency dynamic stretch. This experiment is taken from Wang's group. Here you could see, in absence of external stretch, as I have told you, that cells orient randomly. And from the distribution of the cell orientation angle, you could see the cells do not have any preferred direction. This is but in presence of high frequency external stretch, this is the stretch direction, and cell orient near perpendicular. And from the distribution plot, it's more clear. Now, why cell responds differently in presence of static stretch or compared to dynamic? It remains as a puzzle for many years. And in my talk, I will focus on this dynamical puzzle of cell orientation, and then I would do some theoretical calculation to see this dynamical stretching experiment may be helpful to get an insight to another puzzle, whether the cellular mechanosensitivity is controlled by the force or the displacement of the extracellular matrix. Even yesterday, Margaret has already introduced this puzzle. It's good to think about more about this along this direction. And then I will talk about random cell orientation and competition of stochastic forces with elastic forces. And I hope I have some time also to talk about the frequency dependence of relaxation time. That is how the time to reach to the steady state orientation angle varies as a function of frequency of the external stress. Cells do not rotate as a rigid body like other passive objects. It reorganizes this green dot as the focal adhesion and red as the active stress fiber. It reorganizes and remodels the stress fiber and acting stress fiber and the focal adhesion. This is one of the experiments which shows that in absence of external stretch, the acting stress fibers are oriented in a random direction. Now, when the high frequency external stretch is switched on, then all the stress fibers orient from the random to the near perpendicular configuration after a long time, say 8 hours or so. Now, our model accounts these internal cellular activities of reorganizing the cytoskeleton, reorganizing the focal adhesion and stress fiber in a coarse-grained picture. And also, it accounts the mechanical forces exerted by the matrix. And these together describe the dynamics of the cell, how the cell's contractile force of the orientation changes in presence of static or dynamic stresses. Now, this is a localized force distribution in a cell. The forces are measured at forces exerted at focal adhesion points. These tiny red circles are the focal adhesion, and the blue arrows are the forces measured from the displacement. And now sum of the forces can be described by two equal and oppositely directed contractile forces in mechanical equilibrium. And each cell is modeled by an anisotropic force dipole, where F is the force exerted by the stress fiber and L is the vector connecting the focal adhesions. And since cells are contractile in nature, this force dipole is negative. Now, in general, cells are modeled as a force dipole having force component in all directions. But there are some cells which shows bipolar morphologies due to anisotropic probing. For example, fibroblast or muscle cells. And for simplicity, we consider such needle-like cells whose long axis is along the z direction, and let's assume they are along the z direction, and the force F and L are oriented along the z direction. And in our model, we assume that cell regulates its contractile activity P by the jet component of the force dipole. Now, since cells are contractile, it exerts a large force in the surrounding matrix, and therefore the cells establish a reaction stress in the adjacent matrix. And in our model, we assume, and this reaction stress can be calculated by the Green's function and is proportional to P. And in our model, we assume that cells regulates its contractile forces by reorganizing the focal adhesion and acting stress fiber to maintain an optimal stress to some optimal set point stress, say P star. And this is completely motivated from the experimental observation. Cells taken from solution placed on a gel slowly builds up force and that reaches at some optimal value at long time, which shows the cell measures the local forces surrounding matrix and then regulates reorganizes cytoskeleton to maintain this optimal traction force P star. And motivated by this experimental observation, in our model also we consider that cell dipole regulates its contractile force P to establish a set point stress to establish a reaction stress which is maintained to at an optimal value set point stress value P star. Now any change or any deviation from this optimal stress condition will give rise to internal cellular forces that will tend to re-establish the optimal stress point set point stress again in the adjacent matrix. Now in presence of an external stress of magnitude PA, which is at an angle theta with the cell's long axis, and then there will be an additional force component P cosine square theta. So in our model we assume that cell regulates its contractile activity P, show that the reaction force due to its own contractile activity plus the additional stress, these together are maintained at some optimal set point stress P star. And now the forces can be derived from an effective free energy from the variation of an effective free energy of this kind. Now there are not only the cellular active forces, there is also mechanical forces, and in absence of any external stretch, the elastic deformation energy for force dipole in an infinite elastic matrix is proportional to square of the force dipole, where E is the elastic modulus. So the matrix forces, it will give rise to matrix forces which will tend to change the magnitude of the force dipole, but it is independent of orientation. But the most important, most crucial mechanical energy term is the interaction of the force dipole with the external strain field. And since P is force dipole is contractile, it's negative. So in presence of a tensile stress, it will be minus. The contribution will be negative. And by transforming the strain for Z component, the in terms of stress, that is the P cosine square by E, and this is the total matrix energy. So you could see the matrix force will drive the cell towards, when theta is 0, that is cells are along the parallel to the stretch direction. And intuitively also you can think of like pre-stretch expands the matrix and cell pulls back, cell contract the medium, so pulls back, and overall reduce the matrix strain. And now total effective energy is the cell energy, which is to regulate the optimal set point stress and the matrix forces. And we solve the dynamics of the cell contractile force and its orientation by the relaxation equation. And tau p and tau theta are the time scale, and where tau p is of different time scale. Tau p is the much shortest time scale of the order of minutes or seconds, and which relates the variation of cell forces, and which is much faster than tau theta. You have seen also in the earlier movie that tau theta actually to reach to a steady state orientation, it takes hours of the order of 8 hours or even 3 hours in some experiment. So it's much longer, and so whereas tau p accounts the internal molecular organization, where tau theta accounts the cooperative organization of the cytoskeleton at the scale of whole cell level. Maybe it is important to summarize the parameters in our model. We have one theoretical parameter, that is the chi, which is a measure of cell activity, which is the tendency of the cell to reorganize the cytoskeleton to establish the set point stress. And then we have also other parameters which can be controlled in experiment. For example, the external magnitude of the external stress, its frequency, and the elastic modulus. And also the tau p, tau theta, or P star can be measured in an experiment. Now the steady state calculation shows in presence of a static stress field, the optimal orientation would be theta. As I have already told, there is two pieces of energy, and there is a competing forces due to the cell forces and the matrix forces. Cell forces want to establish the optimal stress point P star, and the matrix force will be balanced when cells are oriented along parallel to the stretch direction. Now, in presence of static stress, cell has sufficient time to relax, so cell can reorganize its contractile forces to establish the set point stress, and thus it balances the cell force, and by reorienting along the stretch direction, it also balances the matrix force. So both the force has time to balance in presence of static stress. But in presence of dynamic stress, the situation is very different. The cell cannot, cells do not have sufficient time to relax, and cells cannot follow the fast varying external stretch. So it can only respond to the time average of the sinusoidally varying external stress. So to predict the long time solution, we average the effective free energy over one cycle, and that gives rise to an additional energy term. And you can see this energy term will vanish when theta is pi by 2. Now the steady state calculation shows that the orientation would be near perpendicular, would be perpendicular when the cell activity term dominates, and when the magnitude of the applied stress is above some threshold value. Actually, the existence of threshold value has been also observed in experiments. This is a dynamical plot of how cellular orientation varies as a function of frequency of the external cyclic stress. We have our theory predict two-step response, and for lower frequency regime, cell orient parallel, as I have told that for lower frequency, when the time variation of the external stress is much slower than cell's own internal relaxation time, cell can balance all the forces. But when the time variation of the external relaxation time is very fast, for a fast varying stress, a cell cannot follow the fast varying stress, because whenever it tries to adjust its contractile force, it sees the direction of the external stress has been changed because of stretching relax and stretching relax. And so cells cannot adjust its contractile activity, and cell gets frustrated. Therefore, it ought to orient to a minimum stress direction where it is no longer affected by the time varying external stress, and therefore can establish the optimal set point stress in its local matrix. But there is also competition with the matrix force, and which eventually determines the steady state orientation. These plots are for two different rigidity of the matrix, and this two-step behavior response actually is similar to a recent experimental observation done in Ken Kummer's group in Stuttgart. Here the cosine twice 2 theta has been plotted as a function of time, and the frequency has been varied for 3 order of magnitude. So you could see for high frequency, so 0 is for the perpendicular, and 1 represents the parallel orientation. You could see for high frequency, cell orients near perpendicular, whereas for low frequency, cell tend to orient towards parallel direction. So now let's switch on to the next topic, whether it will be interesting to see whether this dynamical stretching experiment can be used to understand the cellular mechanosensing activity, whether what controls the cell mechanosensing activity, whether it is force or the displacement of the matrix. In fact, there are some of the experiments which tries to understand what limits the cell activity, whether it is a force control or whether it is displacement control. Now, this is the experiment done in Pune Institute by Saich and co-workers. Here the force exerted, we have measured the force exerted by the cells as a function of rigidity, as a function of rigidity of the substrate, and we have observed the force is proportional to the rigidity of the substrate. And for a simple elastic model, they have concluded should force actually proportional to the rigidity to the cells. So deformation tries to maintain the deformation constant, and cell activity is governed by the deformation of the substrate. Now, but on the other hand, the experiment in MIT by Gibson's group has measured the macroscopic contraction of the substrate as a function of rigidity, and you could see the deformation decreases as the rigidity increases. Now, the force per cell for different rigidity eventually collapses into a single curve which we conclude that the cell mechanosensitivity is actually governed by is the force control, and cell wants to maintain an optimal stress or optimal force in the adjacent matrix. And now in our theory, so what controls whether it is force or whether it is deformation or whether anything else is not clear. So in our theory, we have done a calculation to see whether the dynamic stretching experiment in presence of high frequency dynamic stretching experiment can be useful, can done some experiment to get some insight in this in the cellular to get some insight in cellular mechanosensitivity process. And we have this is for the dynamic high frequency dynamic stretching regime, and we have considered both scenarios when the cell activity is how much time here?
It's around 20 minutes.
Okay. And we have considered two scenarios. One is the optimal strain control, that is cell regulates its contractile forces to maintain an optimal strain in the adjacent matrix. And we have also considered the other scenario where which I have talked about before, the cell control, it regulates or readjusts its contractile forces to maintain an optimal set point stress discharge in the adjacent matrix. Now for the time being, to get the physics in a simple way, we have considered the matrix forces is negligible, that is the cell forces dominates over the matrix forces. Now, in presence of a uniaxial tensile stress, the matrix will be stretched along the stretch direction, but whereas it will be contracted along the perpendicular direction. So between these two directions, there will be a zero strain direction, which is given by which strongly depend on the Poisson ratio. Now, when the frequency of the external stretch varies very fast compared to cell's own internal relaxation time, cell opt to orient to a zero strain direction. And on the other hand, for optimal stress condition, the zero stress for a uniaxial stress, the zero stress condition is basically pi by 2. So you could see in one case, for optimal strain case, where the steady state orientation angle strongly depend on Poisson's ratio, but for the other case, it does not depend on the Poisson's ratio, or weakly depend on the Poisson's ratio. Now, these cases which I have told so far is neglecting the matrix forces, but of course, when there is a competing matrix forces, we have done the full calculation, and this is the plot how the cellular orientation angle changes as a function of Poisson's ratio for two cases: optimal strain case, where cell wants to maintain the optimal strain in the adjacent matrix, and where cell wants to maintain optimal stress in the adjacent matrix. These are for three different matrix forces, but let's focus just for one card. For example, the blue one. So you could see for optimal stress case, the cell orientation angle is orientation angles weakly depend on the Poisson's ratio, whereas for optimal strain case, it strongly depend on Poisson's ratio. So by varying, if it is possible in experiment to vary the Poisson's ratio of the matrix, and then in doing the dynamic stretching experiment measuring the orientation angle, may help us, may give us some insight to understand whether the cellular mechanosensing is force control or stress or strain control. But this is yet to be tested in experiment, and I don't know how easy or how difficult it would be to do. And now I will talk about random cell orientation, and as I have already shown this picture, that in absence of external stress, cells orient randomly, and this distribution plot I have already shown that cells do not prefer any, do not pick up any preferred direction. On the recent experiment again by Kemkemar's group, what they have observed that though for high frequency external stress, cell orient near perpendicular direction, but in presence of low frequency external stress, some cell type shows a parallel alignment, whereas for some cell type, the orientation remain random. So we model this random in our theory. We model these random forces by an thermal type noise with an effective temperature. This effective temperature accounts and is basically a measure of the degree of stochasticity involved in cellular decision-making process, and it accounts all the molecular interaction within a cell and its environment. And now another challenge in this field is to develop a statistical mechanics approach to describe the properties of a collection of cell which is interacting through extracellular matrix. Now, with the simplest approximation, we assume a Boltzmann-like probability distribution for orientation of cell, where F is the scale effective free energy and averaged over one cycle, and Ts is the effective temperature. Now, this is also, some of the experiments have also shown that Boltzmann type of distribution can be used. And here, the probability distribution as a function of, this is the probability distribution of cell orientation for different frequencies and for the different temperature. This dashed curve shows the low enough effective temperature, whether the solid one shows higher effective temperature, and this green to blue to red is in the increasing frequency order. So if we focus for a low effective temperature and low frequency, you would see that distribution has picked up as a maximum near zero. So for lower frequency regime, the distribution is parallel, whereas for high frequency regime, the distribution is a maximum near perpendicular, and which has been observed also in experiment. Now, as the temperature increases, is represented by the solid curve, you could see that for high frequency, the distribution as the temperature has been increased, the distribution becomes broad, and but still for the high frequency, the distribution has a maximum. When the frequency is lower, distribution becomes almost flat. There's no preferred direction. But this will be more clear from the average angle plot. Here, the average angle as a function of frequency has been shown as the temperature has been increased. This blue one is for low enough effective temperature, and you could see from the blue curve for the low frequency regime, the average angle value is parallel, whether for high frequency regime, average angle value is perpendicular. Now, as the effective temperature increases, our theory predicts a very interesting observation, which is similar to experiment. And as the effective temperature increases, you could see for high frequency regime, though the average angle value is near perpendicular, but for the low frequency regime, it remains parallel. This can be attributed, this can be applicable to the experiment which I have shown you, and where people have observed that at low frequency regime, for some cell type, the orientation is parallel, whether for some cell type, the orientation is random. And this can be attributed to the different effective temperature for different cell type. Now I will talk about the frequency dependence of relaxation time, how the time to reach to the steady state orientation angle varies with the frequency of the external applied stress. Now in our calculation, we find two distinct frequency regime. You could see for higher frequency regime, the relaxation time is almost frequency independent. That's because for high frequency, cell cannot follow the fast varying stress, and it can only respond to the average of the sinusoidally varying external stress, and therefore the effective force is independent of the time variation of the external stress, and the relaxation time remains constant. But as the frequency decreases, cell's internal relaxation time plays an important role, and the competition with the driving time scale basically determine the dynamics of the cellular process. And this is the analytical calculation, approximate analytical calculation for this relaxation time, and you could see that this is a very striking similarity, and is qualitatively with a recent observed experiment where for high frequency the relaxation time remains almost constant, and as the frequency lower, and it increases. But one thing here, the important point to note here, that the crossover from high frequency regime to low frequency regime actually sets by the shortest time scale tau p, which relates the time variation of the cellular force and cellular force. And this frequency is scaled with respect to tau p, and when the time variation of the external stress is compared to tau p, this crossover happens. But the value of the relaxation time is scaled by the tau theta, other time scale, is a long time scale, and it's also amplified by a factor at high frequency for elastic, depends on the elastic modulus and external and the magnitude of the external stress, and at low frequency it's amplified by a factor of 1 by omega square. So the main point here is the competition is that we know that cellular processes involve multiple time scale, and the competition between two time scale, one is shortest time scale sets the crossover, and the longest time scale sets the value of the relaxation time. Okay, and I'm almost done. Now it's basically a summary section, and so our theoretical prediction. Our model prediction actually matches with several experimental observations. For example, it could explain the puzzling cellular orientation observation, that is in presence of static stress. Its orient parallel to the stress direction, and Y for high frequency dynamic stress is orient perpendicular to the applied stress direction. Our theory also shows that stochastic forces may play an important role to set the steady state orientation, and our theory predicts the existence of a threshold stress, and which shows that cellular response is nonlinear, and also our theoretical calculation shows that this dynamic stretching experiment may be useful to get some more insight in the cellular mechanosensitive activity, for example, which I have described as a force versus displacement concept. And our model is a macroscopic model, is a coarse-grained model, but it was able to capture the multiple time scale involved in the cellular process. And but to understand from one, of course, I agree that one need to build up more microscopic models modeling the focalization and stress fiber to understand the detailed interplay of the time scales. And thank you for your attention, and I'll be happy to.
So we have ample time for discussions. Any questions?
Yes.
The Poisson ratio prediction. So that's a prediction for a specific kind of measurement.
But you have a physical model for the cell. So could you make predictions about just generic cell behavior on substrates of different Poisson ratio outside of a cyclic stretching experiment?
No. Actually, if for the statistic, if the frequency is low enough, then in both cases it will be oriented parallel to the stress direction. So it won't give any information about whether it is stress deformation control or force control. But in case of high frequency dynamic stretching, I don't know whether I can explain it properly. As I have told you, the cells do not follow the fast varying stretch, because whenever it tries to adjust its contractile force to establish the optimal force or displacement, whatever it want to maintain, but it sees that since the stretching force is very fast compared to cell's own internal relaxation time, it cannot adjust its contractile forces. And it sees the external stretching has been changed, and the direction of the external stretching has been changed very fast. So cells get frustrated and they opt to orient in a direction where it won't be affected by the external stretch, or affected minimum amount of external stretch. And for strain, it will be the minimum strain direction if it wants to maintain an optimal strain. And for stress case, if it wants to maintain an optimal stress, it will orient to a minimum stress direction. And you could see for a uniaxial stress, our calculation shows the minimum strain and minimum stress direction are completely different. One is strongly dependent on conscious tissue, another is weakly dependent. So that might help.
But only at high frequency.
Only high frequency, yeah. But it's on more. within the scope of our model.
So can you explain in physical terms the mechanism why this energy is as a minimum at high frequencies at 90 degrees?
Okay, that's because I'll go back to the energy expression. So in our model we have two sources of energy. One is the cell activity. What is the cell activity does? It wants to regulate this contractile force P so that this optimal stress P star is established again. So once it can establish P star, the cellular force balances, P star balances. Now the next term which remains, you could see when theta is 0, this is a matrix, interaction energy of the force dipole with the external field. And now when theta is 0, you could see the energy is minimized. So that will, so the force derived from the variation of the field energy would drive, matrix force would drive the cell towards parallel to the stretch direction. But on the other hand, when the frequency is very high, means when it is the time variation of the applied stretch is faster enough, is much faster compared to cell's own internal relaxation time to adjust forces to establish the P star. So therefore it cannot respond, it cannot follow the external stress, and it can only respond to the time average. And if we in our theory we wanted to capture the long time solution, and so what we did, we had this effective free energy we have averaged over one cycle. And if you see the applied stress, this PA is basically stretching relaxation, so that will give a contribution, additional contribution because of the averaging, because we have to average the cosine squared theta, and that has a finite contribution, and that will give rise to a positive term, if you see this term. And this term will vanish. You could see when theta is pi by 2, this is 0. That's the perpendicular one. But it's the steady state, we have done the steady state calculation, so this will be stable, perpendicular calculation will be stable if the value of the chi, that is the cell activity or the tendency of reorganization of cytoskeleton is high enough compared to matrix forces. And also there exists a threshold value of applied stretch magnitude. So that when, in other words, when the contribution of this term is very high compared to the other term, cells will be directly.
So do I understand correctly that basically the mechanism is that when you do the dynamic stretching and contracting, you spend energy on both ways, but if you have to polymerize and depolymerize, and that additional energy, and the cell tries to minimize that, so when it orients perpendicular, it doesn't have to spend this source energy by building and
exactly.
So
exactly. When it is in the minimum strain direction or stress direction, yes.
Because it spends energy both ways, so it goes like stress, contract, and
Right.
Yeah. My question was, again, in the static stress field or zero external stress field with just a substrate, could you predict that a transition being strain control to stress control just by simply modulating the internal contractile force of the cell to the external matrix stiffness?
With the stiffness dependence?
Yeah.
No, actually that is not very clear. And you know what we have done in our calculation? It's basically the force cycle is a point force, and this is the effective elastic modulus. I think one need to do a rigorous calculation for mechanical calculation. So that's actually we want to do on the two substrate level. No, so your question is no, I cannot answer for the stiffness.
Right near the end, when you have the relaxation time as a function of frequency, your theory at small frequencies said it went like 1 over omega squared.
Yes, approximately, yes.
So in the experiments, there was also a power law, but what was the exponent of that power law? And what does that exponent tell you?
That is a good question. So if you see, so I have told it is only qualitatively similar, not quantitatively. And the plot I have shown is for an approximate calculation. This is an approximate analytical calculation and this plot. So in their case, if you see, it's almost linear. But again, we have discussed with Ralph Kemkemer. So what he has to do, if you see, he has only varied 3 order of magnitude. And in experiment, I think if they could have varied for more, like 10 to the power minus 10 to the power minus 4 or something, we could go to the lower regime. Perhaps this whether now it's a question whether it's a linear dependence or it is something it's still unclear. So my answer would be in our theory could capture the high frequency regime, and for low frequency it can only say that it increases, and also it can it shows the time scale, the value of the relaxation time also it matches with the experimental condition. But your question of exponent, whether we can match with the theory and experiment, so
okay, but does that, like, is there some, does that exponent not matching, does that sort of does that exponent tell you something about the physical system, about these different sort of time scales?
Perhaps yes, but then I think one need to see it's our model is a coarse-grained model on a more macroscopic. We have not captured the microscopic phenomena. All the microscopic phenomena of reorganizing cytoskeleton has been captured in the cell activity of, say, maintaining optimum stress. But even it could capture this multiple time scale, that crossover and the increasing. Like the crossover depends on the shorter scale and the value depends on the longer time scale. So one need to answer, so the answer of your question is to understand that one need to model from microscopic point of view to exactly, but I am sure that it will give some more information.
Any more questions? Well, let's thank the speaker again. Thank you very much.